Hello and welcome to this video on reaction rates, where we will be studying the reaction between carbon dioxide and water to form carbonic acid. So the first thing we want to do is we want to know what kind of kinetics we're dealing with. So we're going to start by writing our general differential rate law. So our differential rate law says that the rate of formation or change of H2CO3, carbonic acid, equals the rate constant K times the concentration of carbon dioxide to the M power and the concentration of water times the concentration of water to the N power. So how do we determine M and M? We are going to need to look at some data. So here is some data I have on the rate of formation of carbonic acid. And so we see here that we have a rate without an enzyme and a rate with the enzyme carbonic anhydrase. So we're going to need to look at some data on the rate of formation of carbonic acid along with the rate constant and concentrations of carbon dioxide and water. So let's look at two scenarios. So when we double the concentration of carbon dioxide and keep a constant concentration of water, we see that the rate doubles. So we're going to look at lines 1 and 2 here. So lines 1 and 3 here. So we have constant concentration of water, and we've doubled the concentration of carbon dioxide, and our rate has doubled, which means that the exponent m equals 1. We're going to do the same with water. So we double the concentration of water while keeping the concentration of carbon dioxide the same. And again, our rate doubles. So we get n equals 1. So now we're going to rewrite our rate law. So we've rewritten our rate law to include these exponents m and n. And we want to ask ourselves, what is the overall order of the reaction? So we add the exponents and we get 2. Now, so we see that the reaction proceeds kind of slowly without an enzyme, but then when we add an enzyme, carbonic anhydrase, that should be an S here, the rate increases dramatically. So in the human body, this reaction is catalyzed by the enzyme carbonic anhydrase. And so let's just explore what this enzyme, or how this enzyme sort of affects the reaction rate. So carbonic anhydrase has a high affinity for carbon dioxide and water. So we get carbon dioxide and water binding to this enzyme. This enzyme changes shape, and it brings the two molecules, carbon dioxide and water, closer together and stabilizes the transition state. So this enzyme, carbonic anhydrase, is an example of a catalyst. And so what this does, in addition to bringing the carbon dioxide and water closer together and stabilizing the transition state, what it really does is it lowers the activation energy, which means that the reaction can take place at a faster rate. So let's draw a reaction coordinate diagram for this reaction and see what it looks like with and without this enzyme catalyst. So we have this reaction coordinate diagram, and we start with our reactants. And they have a certain amount of energy. And then we end up with our one product which our one product is carbonic acid. So we can talk about something called the activation energy, which I mentioned earlier. And so the activation energy is the energy required to bring the reactant, from the reactant state to the transition state. Now, what an enzyme is going to do, or any catalyst really, it is going to lower that required energy, that activation energy. In the human body, we can't really sit around and wait for many of these reactions, especially an important one like this. This is regulating blood pH and its respiration. It's just involved in generally maintaining our human condition, properly maintaining it. So we have these enzymes in our bodies that make these reactions go faster by lowering the activation energy. So thank you for watching, and here is my works cited.